flare, releasing an outburst of X-rays that can reach Earth within minutes. The second, more ominous threat arrives a few days later, a phenomenon called a coronal mass ejection, or CME. It's a wave of billions of tons of electrically charged particles, seen here in this repeating image as it ripples away from the eye of the storm. Together, they could hit like a cosmic tsunami. Delivering a surge of radiation and an electrical spike of trillions of watts, potentially crashing the power grid. Sound far-fetched? In March 1989, in Quebec, Canada, that's exactly what happens. One by one, power stations crash, disabled by the overwhelming power surge caused by a CME wave. In less than 2 minutes, 6 million people are left without power. Recently, NASA's Jim Green finds evidence that an even bigger solar storm hit Earth in 1859.
And what we found was the granddaddy of geomagnetic storms, and that was just 150 years ago.
The reports tell of auroras, brilliant displays in the sky. They're so bright that miners in Colorado wake up and go to work thinking it is dawn. Other reports tell of a more harmful impact on the lone electrical system of the day, the telegraph.
One, for instance, because of the induced current on their system, overheated the battery and started a fire, nearly burnt down the telegraph office. Another operator was burnt so badly he ended up into the hospital.
Green uncovers numerous reports of auroras seen not only across the United States, but around the world. The evidence is clear. Earth was struck by a superstorm in 1859, the result of 2 massive CME waves.
Those 2 storms were not only enormous, but they happened one right after the other. No one alive has seen anything like it.
If we had a geomagnetic storm of that intensity today, the National Academy suggested that the impact on critical infrastructure could be catastrophic. And the big concern is the electric power grid.
The massive electrical surge from a CME wave could overload power lines and melt transformers, blacking out entire cities.
Repair could take weeks, months, and even in a worst-case scenario, the National Academy suggested up to 10 years for a full recovery.
If that occurred, if you can imagine a world without electricity, you're really going back in time.
It's not just the power grid that's at risk.
More and more, we rely on technology that could be affected by the sun. Global positioning satellites, long-distance communications, airplane tracking, astronauts in space.
Roger, how does it look?
So there's an urgency in understanding what it is that the sun is doing, what's it going to do next, and how can we prepare for that and respond to it.
Worried or not worried?
Well, I would be just a little bit worried, given concern right now. We'll be watching and monitoring it very closely here in the coming days.
We've gazed at the sun since antiquity. We've worshipped it and built entire cultures around its power. We marvel when it's eclipsed during the day. And when its power lights up the night sky with dancing curtains of light, the aurora. Its power and size are awesome. It is so huge, 1 million Earths could fit inside it. Temperatures at its core soar to 27 million degrees Fahrenheit. It's been shining for over 4 billion years, and will do so for at least 4 billion more. Yet for something that has such an overwhelming influence on our lives, the sun is mysterious. How does the energy generated in its core reach us as sunlight? What processes are at work inside the sun? How do these powerful inner workings generate explosive solar storms? These are some of the mysteries scientists must understand to protect us from the sun's darker side.
The sun can really surprise us.
The sun is elusive,
Crazy,
Complicated.
crazy,
Incredibly dynamic.
crazy.
With explosive potential.
The key to that explosive behavior lies deep beneath the sun's blinding surface. Until recently, seeing inside the sun was impossible. Understanding its internal processes, a pipe dream. But an accidental discovery changes everything.
Until the 1960s, much of solar physics relied on things that were like solar dermatology. It was things that were right at the surface or just skin deep.
But as physicists study the sun in more detail, they make a surprising discovery. The surface seems to be vibrating, like ripples on a pond. Initially, they think the vibrations are the result of defective instruments.
They couldn't get rid of them. They built better instruments, the ripples were still there. They looked at it for 10 years, and they did conferences, they all talked about it, and they harumphed. But what it turned out to be was just sound waves.
It is an astonishing revelation. No one expects that the sun can generate sound waves. It leads scientists to see the sun in a completely new way. Our sun vibrates like a giant pipe organ. But instead of air producing the notes, churning gases deep inside send sound waves rippling through its interior.
Because a sound wave changes as it moves through different material, we can look at the different frequencies and determine what's happening inside the sun.
Geologists are familiar with this. By studying sound waves passing through the Earth's crust, they can see the layers below our feet. A technique called seismology. Similarly, sound waves moving through the sun's interior reveal how it's made up.
I can use this organ to illustrate how sound waves work inside the sun. For example, if I hit this low note, it comes from one of these big pipes, big deep sound. And on the sun, that corresponds to a wave that goes very deep into the sun and brings back the information. If I turn to a high note, it comes from a much shorter pipe, and on the sun, that's telling us information about very close to the surface of the sun, not very deep at all into the sun.
There are 10 million different frequencies resonating in the sun. Deciphering them leads to a seismic shift in understanding its structure, creating a new science, helioseismology.
Once the helioseismology came along, we could not only see what the surface was, but we could actually tell what the physical processes were underneath. So By looking inside, we can actually see what the sun is doing.
It is a powerful tool to see beneath the sun's surface. Studying the sun's sound waves reveals a complex, multi-layered machine. Directly beneath its blazing surface is a zone of perpetual churning. Next is a layer where light takes thousands of years to cross. At the center is the sun's core. It's the smallest region, but it's over 25 times the diameter of Earth. This is the powerhouse of our star. Everything we experience on Earth, sunlight, heat, and the effects of solar storms, starts here. So what's it like here? What's the core made of?
Well, the sun's a crazy place, right? It's far too hot to be a solid. We know that. Right? Heat it up, it's far too hot to be a liquid. And so you think, well, it's a gas, right? Well, not really. It is this gaseous soup of charged particles that we call plasma.
You're more familiar with this soup than you might think.
There are plenty of examples. Fluorescent light bulbs, flames, neon lights, perhaps fancy TVs that I can't afford, but these are all plasma. Plasma is sort of all around you.
But plasma is radically hotter at the sun's core. The closest thing on Earth is lightning. During thunderstorms, electric charges build up, creating lightning bolts that reach tens of thousands of degrees.
That's pretty hot, but it's nowhere near as hot as in the core of the sun. So if you were to travel into the core of the sun, the plasma would be 15 million degrees.
As the sun formed, hydrogen gas at its heart was crushed under the weight of the material above. Eventually, temperature and pressure rose so high, the hydrogen atoms broke apart into electrons and protons, creating plasma.
And it's under these extreme conditions that something really, really cool happens. Nuclear fusion.
It's the same atomic process inside the hydrogen bomb. Under tremendous pressure, protons in the plasma fuse together, releasing photons, minuscule packets of heat and light. An unimaginable number of photons are made every second, generating the sun's incredible power, some of which reaches us as sunlight. This atomic alchemy converts over 4 million tons of mass into energy every second in an endless loop.
That much mass into energy is the equivalent of 10 billion hydrogen bombs being created every second. The sun does this day in, day out. It's been doing it for 4 billion years, and it's going to continue to do so long after I'm gone.
The energy of billions of bombs is released in the core every second. This begs a simple question.
So you could ask, well, why doesn't the sun blow itself apart? It's because there's this beautiful balancing act that occurs. In the core of the sun, you've got this pressure from all of this fusion pushing outwards. And the sun is huge, so you have all this gravitational pressure pushing downwards. And so you've got gravity pushing down, and the sun trying to blow itself apart from the inside, and it is this beautiful balancing act between the two that keeps the sun in one piece.
This light, born at the core, reaches us after a remarkable journey. Away from the core, pressure and temperatures drop, and nuclear fusion stops. Now, each photon begins a tedious journey through the sun's thickest layer of plasma, a region called the radiative zone. Although squeezed less than at the sun's center, the plasma is still very dense, and photons struggle to move through it. Each packet of energy is continuously absorbed, then spit out by the plasma particles.
In that particular part, there's no energy being generated, but the energy is transmitted by the radiation. So that's why we call it the radiative zone, not too surprisingly.
The photons slowly bounce through the plasma here, ricocheting in a zigzag path called the random walk.
So imagine that you're in a crowded room and you're trying to make your way through, and you greet other people. And each person you greet, you have to say hello to, and then you move off in another direction. So it takes you a long time to get from one place in the room to another because you're just kind of meandering your way around the room. So the same way the photons in the inside of the sun, they don't have a preferred direction. All they want to do is they want to be moving, and they want to be greeting other particles.
Though moving at the speed of light, 186,000 miles a second, it takes photons over 100,000 years to cross the zone. Eventually, the photons reach a boundary where pressures drop again. The plasma thins, and moving through it gets easier. The photons still pack a lot of energy. Now, they leak out into the convection zone, heating it from below. The thinner plasma in this zone makes the photons move in a different way.
So instead of bouncing, all of a sudden there's an ordered motion. So it's as if all of a sudden someone said, lunch, and all the particles decided, oh, we all have to go this direction. You still have to wait in line to get out, so it takes a month to get from the bottom of the convection zone to the surface, but it's a relatively short period.
During this short period, heat from the photons sends plasma here into perpetual motion, a maelstrom of churning 125,000 miles thick. Think of it like a massive lava lamp.
There's heat that enters at the bottom from the light bulb. It heats the material, and the blob rises to the surface. When it gets to the top, it cools off. And when it cools, it gets more dense and falls back down. This is a good analogy for what's happening inside the sun. We have the core of the sun heating the material at the bottom of the convection zone. The material expands, and it carries the energy upward until it gets to the surface.
These incredible images reveal convection at the sun's surface, rising and sinking plasma that creates a mesmerizing structure called granulation.
The granulation cells are about the size of the state of Texas. They only last for about 12 minutes, so there's an incredible amount of energy. It's a very dynamic, very chaotic place. And all of the activity is going on the surface of the sun where we can see it.
Photons produced at the core finally reach the surface. They emerge as a weakened form of solar energy. This weakened energy reaches Earth in 8 minutes. We know it as sunlight.
So 100,000 years, about a month, and then 8 minutes. Once you get to the surface of the sun, it just takes 8 minutes to get to where you can see it.
Unimpeded, the trip from the core to the surface would take the photons a matter of seconds. In reality, the sunlight that shines on us today may have been created during the last ice age. Energy reaching the sun's surface doesn't just result in sunlight. It can also trigger solar storms. Understanding the sun's destructive power requires 24-hour precision surveillance, something that, until recently, was impossible to achieve.
5, 4, go for main engine start. 3, 2, 1, 0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory.
February 2010. NASA launches its most sophisticated solar satellite yet. The Solar Dynamics Observatory, or SDO for short.
Coming up on Mach 1.
SDO is the first satellite to deliver almost continuous, super high resolution coverage of our nearest star, giving researchers unprecedented access to the sun and its secrets.
The first day was very exciting. We knew we were going to open our doors that actually let the sunlight into the instrument for the first time.
We started looking at the first pictures, and it was almost in focus. And as soon as we focused it, it was just beautiful.
The new images reveal the sun like never before. An alien landscape where strange structures ebb and flow. Giant tornadoes, hundreds of thousands of miles high, that could easily engulf the Earth. And superheated bubbles of plasma the size of Alaska.
When I look at the pictures, I think they're really beautiful. I'm struck by the dynamics of it. Things are changing all the time, no matter where you look. And I'm also pretty daunted by the complexity of it all.
That's not surprising. Previous satellites only revealed